Okay, yes, thanks everyone for being here. Okay, so the last week and a half, I've been focused on kind of looking a bit deeper into the ETH-Stack documentation, looking at a lot of different materials to kind of get an end-to-end, I call it the life cycle of a Stack proof. Basically, the end-to-end construction of a Stack proof. I have to say that this is still a work in progress. So I think at the end, my goal would be to have like a one-pager of the entire construction. So there will a few things that might be a bit simplistic. There will a few things where I might have to go a bit quick, also considering the 50 minutes that I have today. But generally, there will be four steps, which will be, the first will be the execution trace. I think we're all pretty much more familiar with that now. Then the second one will be the encoding of the trace using the Reed-Solomon encoding, where we go from columns to trace blocks. What exactly that means, you'll see in a second. This next step will be the constraints. Essentially, in this case, since we're working in stacks, it will be the AR. And just to give you this will be a part where I'm going to be a bit more quick. So this is going to be more of a black box for this talk. But then the last part will be Fry. And I take a lot of part here because this is going to be also split into a few parts. I think we're all also familiar with that at this point as well. The splitting, the mix or fold, the commit, and then the query. Okay, so this is going to be the whole talk of today, where again this is going to be in a box for today, the constraints part. Okay. Okay. So when we first talk about execution trace, I want us to be clear that we talk about a table. I think in any system, we have, this could look always different, the different kind of systems. But in this case, I'm doing it like where we have a clock with different kind of time steps, where we have T1, T0, T1, T2, and T3 in this case. And different kind of variables, different kind of data columns that change over the state of different kind of t's. So I'm just going to call these x0, x1, x2, and x3. So I think what I've learned, especially the last week, is why polynomials in this case are so helpful. Because we're essentially able to take one of the columns of one variable and essentially create a polynomial that represents the state changes of the variable over t. So the goal is to create a polynomial. Yeah, I'm going to do a lot of writing here just because I want this to be that represents v1 over t. And in the risk zero, they're using something called INTT. I'm sure there must be different kind of methods, but this is how we essentially get a polynomial that in the end looks very similar like this, where we have the polynomial of m of 1 over xi that computes to the trace table section of, I think this is I guess it is, yeah, okay. So this is t of I over the variable. In this case, we chose f1. Okay, so this is how we start. We want to create that kind of polynomial which essentially represents the state changes of this variable. So actually now we look in columns, and what's going to be interesting, what we're going to do now, actually, we don't really operate in a field of just integer numbers, so we actually operate in a field of finite fields. So for this example, I'm going to use a very simplified finite field, f over 41, where I'm just going to lay out all these terms because we need all of them later. I'm just going to use an operator of 6, and we're going to work on the 8th root of unity. So it will look something like this. 8th root of unity. Because this is actually something we're going to need now also for the Reed-Solomon encoding. Because what we're actually going to do is we're not only going to take those values, we're actually going to take the omega. And the omega we compute actually now, which is the generator to the power of p minus 1, which is in this case the 41, over n. And that's specifically going to look like this. This is going to be 41 minus 1 over 8, which in this case is going to be 20. I'm just going to kind of put these terms in here, just so we have a better understanding how this is actually constructed. And now I'm going to talk about why we actually need the root of unity. Because actually, if we use these, we don't really operate on these normal values that the execution table has. Actually, we're going to map them to the root of unity, to the power actually. There are different ways to do this, but this is just the simplified way I've chosen. Okay, so now we're kind of mapping the different values in the table to the different kind of values of omega. And now this polynomial actually looks a bit different. So this polynomial now looks not over x, but it actually looks over the power of omega. But aside from that, it looks very, very similar. Okay, so now we kind of have everything we need from the execution trace. But obviously, we need to encode it. That's why we use the Reed-Solomon encoding. And what we do here, okay, now I have to, the whole goal is in the end to have a trace block that we can actually, that is this encoded, that's the encoded version of the column. Because again, we do it all on this one column. All of the things I'm doing here, we would do for every single variable. And actually, what we're going to do here, that's pretty smart, what's part of the Reed-Solomon encoding, we're going to extend the domain. Because this is in case our domain, but we actually want to extend it. I'm just going to call it d star, whatever. Where we actually add more and more values. Remember again, this is a very small prime field. This, in a real use case, will be a lot larger, so it will be a lot more complex. But I'm going to add 6. Okay, so we're just going to add, we're going to extend our domain, so we have a lot more values of omega, which we will actually use now to construct the first commitment. Okay, now I have to say the caveat here is that actually it's not as simple as this. There's this big black box, which is the constraint part actually. Because we wouldn't commit directly before we go to phi, we wouldn't really commit that on the trace polynomial. Here would be the boundary constraint, we would have the transition constraint, and then all the different trace polynomials that we're kind of constructing here. And all of those, we get, at least in RISC-0 documentation, we would get different kind of deep polynomials, they call it. I'm sure that different kind of terms for other different kind of literature, but this is what they're using. Okay, so now we have all these different polynomials, we turn them deep polynomials, and then in the end, we actually get the Frey polynomial, which is a batched version of all the deep polynomials. Okay, I'm just going to write very quickly here. Okay, so why is that important? Actually, because we need all of those values for the first commitment. So the way it's going to look like, I'm just going to call this Frey polynomial f0 over x, where essentially we create a first commitment, not f0 over x, but actually over all the omega values. So this would be omega to the power of 0. This would be omega to the power of 1. Omega f to the of omega. I'm just going to try that. Okay, it's a bit. Yeah, okay, I still have enough space. 6 and 7. And this is actually going to be our first Merkle commitment in this simplistic kind of view. There has been a lot been before, but I just want to simplify. Wait, sorry. Okay, so this is now would be our commitment of the Frey polynomial. Again, there's a lot of things that are happening here that I'm kind of glossing over right now. And my goal at the end of the next week would be to have an end-to-end. So also taking all the constraints, looking at all the boundary constraints, additional constraints, and then actually getting from the deep to the Frye polynomial. But this won't be the session of this talk, because what I actually want to do now is I want to finish Frye on this commitment. Because actually what we're doing right now, we're only committing the Merkle root in this case. And that's actually what we have right now, this what we always have been looking at, the P and the verifier. I'm leaving this for the query section actually. Because as a prover, we're going to firstly commit the Merkle root of this Merkle commitment. We want to show now that this polynomial has a low degree, and for the verifier in the end to actually validate all the different kind of points at evaluation. So I'm gonna what do we call this? I'm just gonna call this the commitment of f0 over x. And then the verifier, what he would say it's too large. He would send back R1, which is a random value. And then actually we start with the splitting, right? I think this is something we're very familiar now, where we have now this polynomial. In my case, I'm just going to say it's of degree 7, which also corresponds, by the way, to the root of unity, which is not just by coincidence. So now we would have a polynomial that looks like this. Plus a6, x plus 6, plus a7, x to the power 7. Okay, so this is our Frye polynomial in this case. And actually we're going to split it. I think we're all very familiar with what it looks like. I'm going to call this f0. f0, the splitting looks like even x plus x times f0 odd over x. So this is how the splitting works, right? So we just starting to split it, but obviously then we also want to fold it. Just for the first iteration, I'm actually going to write out what these look like. So what the even polynomial looks like. So this would actually look, we take the even numbers, which in this case is a0, a2, a4, and we start incrementing the coefficients.
A2x squared.
I mean, we're bringing down the degree in this case. So yeah. So no, it will look like this. We'll see in a second, because actually we're taking it out here. So if we were to calculate this out, this would again return to the original polynomial, but we're splitting it. So this would look like a1, a3, a5, and a7. Okay, so now we split the degrees. And now the batching, the mixing and folding, whatever we call it, we use the R1, which this is just the first iteration. We then will have our F1 polynomial, which is going to be F0 even of x. I'm not going to write it out. So it's going to be this polynomial plus R1 times F0 odd to the power of x. So actually we've taken this long polynomial and we split it by 2. Actually in risk 0 they actually don't split by 2, they split by 16. They have like way larger, but in this case just a simplified version again. So anyway, so now we actually lowered the degree from, in this case, 7 to 3, and we added the randomness from the verifier. And this will be our new polynomial on which we can actually make the Merkle commitment. So this one is actually going to look very similar, but instead we don't use f0, we use x1, and we use it on, we have to also split our evaluation domain, which is actually going to look like this. And F1. Yeah, I'm glossing over a lot of things just because in respect of time. And we do the same thing again. And we have our new commitment. And again, we only commit the Merkle root, again, to the verifier. And the verifier again is going to say, hey, this looks way too large. So we actually want to go down as to a constant in this case, which is kind of what I just want to represent. So we got back to the prover with, God, this looks really messy, with R2. And I'm not going to take all the stops again, but what it would look like in the end is that we will have an F2 where we make a new Merkle commit with, again, it's 1. We're going to send it back over again. And at the very end, we will actually have we won't Merkle commit again, but we'll just go down to the constant just to prove that it's low degree with an F3, where again, it won't be at this kind. We don't have it will actually be constant, and it will look like this. 1, 2, 3, 4, 5, 6, 7, 0. So this is the constant, which is essentially being shrink down all the way from a degree 7 polynomial all the way to 1 constant. And in this case, we're going to send it over again to the verifier, and the verifier is going to say, that's fine, okay? Now I actually want to go back and actually make sure that all of the steps you've taken are actually correct. And so we have one for the splitting phase, we want to mix and fold to the commit, and now we're here. And what the verifier now does, he says, okay, I want to evaluate at a specific index. So in this case, I'm just going to choose index of 2. I'm for sure there also goes some intuition to why you choose in a specific subset. But now the verifier, the cool thing about this is that the verifier would essentially, just giving us this index of 2, he can request all the different evaluations at this index from the prover. And the prover is going to give both all the leaves of the Merkle commitment plus the authentication paths. And obviously we have also all the previous Merkle commitments, Merkle root commitments. So with all this information, the verifier can already locally verify all the different kind of previous computations, which is really cool. He doesn't need any more information. And the way this works is basically we can use, okay, I have to remember this. We can recompute, or for example, we can recompute the value of f1 over x to the power of 2 by actually going back and looking at the previous round. In this case, it would be like this. R1, the verifier knows because he sent it. This is odd. And this is x power of 2. Okay, so this is just the foundation of how the verifier now can actually, with all this information, can actually go back and verify all of these different steps. And I'm just going to break it down a bit further. Wait, okay, this is what I want to say actually. I just want to break this down a bit further so it's a bit more clear of how we're actually doing this, because now we're actually still working in the power of 2. So actually, this is going to look like this. 0x plus, and remember those x's are actually also still the omegas that we've been using before. I'm just going to write it down here. Okay, I think I'm almost done. Okay, and remember, so at the two different indexes, the way I understood it, correct me if I'm wrong, is we would essentially prove it at the index 2 of each different Merkle commit. We get the leaf and we get the identification path to exactly that index. And then we can actually also insert in these points, we can insert the different omega values based on this equation. So in this case, x is actually omega, which is the same as before, to the 2 to the power of k times the index. So k, for example, in this case is 1, but here in this case it's 0. So it depends on which round we're at right now. And this is basically with all these kind of steps and the different kind of, the interesting kind of properties of finite fields within this entire construct, the verifier can actually verify of the previous commitments that we've done from the very beginning. The moment we commit, we bound it to the commitment. And if everything has been correct, we've both tested the low degreeness of the polynomial and all the different variations that we've done previously. And that's how we've now done the query part as well. And that's my life cycle of a Stark proof, where we went from the very beginning of the execution trace, where we've looked at the execution of a variable, all the way to the Frey polynomial, and then actually going through the different steps of the Frey protocol, which includes the splitting, mix, unfold, commit, and the query. Again, this is a work in progress and a bit of a simplistic view, but for me it was important to get an overview of the entire STEM process, and I hope I was partly also able to do the same. The goal was to have in the end like a finalized one-pager, so I was writing a lot, and I hope that helps. But yeah, thank you for listening.